Hello and welcome to this video about matrix proofs. There are 4 parts to this proof. Multiplication is a bit more complicated than addition for matrices. We'll use this ijth entry notation for all of these parts of the proof. So now to prove part A. We'll start with the left hand side and convert it to ijth entry notation. We can bring these entries into the same square brackets because it's the definition of addition. Now to bring in the third entry, which is multiplied by the other entry. We need to use this sigma sum to describe what it is as the ijth entry in this matrix. This is the definition of matrix multiplication. It looks complicated, but we can still work with it. Then we can expand the round brackets to get this expression. Then we can split this sum into 2, but keep these sums in the same square brackets. Now we can separate this expression into separate matrices, but still in ij entry notation. Because this is the definition of matrix multiplication, we can work backwards to get this expression being the sum of 2 matrix products. And then finally we can write this out using the matrix variable names. And so we've completed part A of this proof. And now to prove part B, which is the expansion of brackets, where the single matrix is on the other side of the brackets this time. This proof should be very similar, but different enough to make it worthwhile to explain it. So now to prove it. We'll write the left-hand side in ijth entry notation. We'll expand the square brackets to include both expressions. We don't need the round brackets for the moment, because there's no need to show which operation is done first. We can expand the square brackets to include the matrix A. This is what the product is in terms of these matrices using this entry notation. We can then expand the round brackets inside the sigma sum. Then we can break up the sigma sums into 2, but still keep them in the same square brackets. Now we can separate the square brackets, which is like representing 2 different matrices added together. We can use the definition of multiplication to separate these matrices into the product of 2 matrices added together. And then finally, we can represent the matrices using their variable names, thereby completing the proof of part B. And now to prove part C, which is the product of 3 matrices and therefore looks more complicated to calculate. There wasn't any proof given for this in the textbook, so I had to do it on my own. So we can express this product in ijth entry notation. And we can use the definition of multiplication to bring the 2 matrices inside the square brackets into the same square brackets. And then we can use the definition of multiplication to bring the matrix C inside the square brackets. I had to introduce another counting variable L. You can see where the I and J variables are. So this is the expression for the ijth entry in this product of 3 matrices. These index variables are fairly independent of each other, and so we can gather them all together like this. Then we can swap the sigma sum so that L is inside the round brackets and K is outside these brackets. We can take variable A outside the inner sigma sum. We can use the definition of matrix multiplication to separate the square brackets to get a product of 2 square bracket expressions. We can use this definition again to get the product of 3 matrices in ij entry notation. And then finally, we can write these matrices using their variable names, with the brackets around the last 2 variables, thus completing the proof of part C. Now to prove part D, which is a proof of multiplication of matrices using both sorts of matrix multiplication. So we'll convert the left-hand side into ijth entry notation. We'll use the definition of matrix multiplication to get this expression inside only 1 pair of square brackets. We'll use scalar matrix multiplication to get the scalar A deep into this sigma sum straight away. We can easily swap the brackets like this. We can reverse the definition of matrix multiplication to get this expression. We can get the scalar A outside the square brackets, but put these entries inside round brackets to show that they must be multiplied together first. And then finally we can write this expression out using the matrices variable names, so as to get the central expression that we're trying to prove. We can start off with this expression so as to get the expression on the right hand side of what we're trying to prove. Because these are numbers, we can bring the scalar a next to b with brackets around it like this straight away. We can use the definition of multiplication backwards to get this expression. We can take scalar a outside the square brackets like this. And finally, we can write this expression out using variable names, thereby proving part D of this proof, and so we've proven the whole theorem. So I hope that you've found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to post any helpful comments and to share this video. And thanks a lot for watching.